MIT engineers have created soft 3D printed structures whose movements can be controlled with a wave of a magnet, much like marionettes without the strings. The list of structures that can be magnetically manipulated includes a smooth ring that wrinkles up, a long tube that squeezes shut, a sheet that folds itself, and a spider-like grabber that can crawl, roll, jump, and snap together fast enough to catch a passing ball. It can even be directed to wrap itself around a small pill and carry it across a table. The researchers fabricated each structure from a new type of 3D printable ink that they infused with tiny magnetic particles. They fitted an electromagnet around the nozzle of a 3D printer, which caused the magnetic particles to swing into a single orientation as the ink was fed through the nozzle. By controlling the magnetic orientation of individual sections in the structure, the researchers can produce structures and devices that can almost instantaneously shift into intricate formations and even move about as the various sections respond to an external magnetic field. This technique may be used to fabricate magnetically controlled biomedical devices. For example, we could put a structure around a blood vessel to control the pumping of blood, or use a magnet to guide a device through the GI tract to take images, extract tissue samples, clear a blockage, or deliver certain drugs to a specific location. You can design, simulate, and then just print to achieve various functions. The team's magnetically activated structures fall under the general category of soft actuated devices, squeezy, moldable materials that are designed to shapeshift or move about through a variety of mechanical means. For instance, hydrogel devices swell when temperature or pH changes. Shape memory polymers and liquid crystal elastomers deform with sufficient stimuli such as heat or light. Pneumatic and hydraulic devices can be actuated by air or water pumped into them, and dielectric elastomers stretch under electric voltages. But hydrogels, shape memory polymers, and liquid crystal elastomers are slow to respond and change shape over the course of minutes to hours. Air and water-driven devices require tubes that connect them to pumps, making them inefficient for remotely controlled applications. Dielectric elastomers require high voltages, usually above 1000 volts. There is no ideal candidate for a soft robot that can perform in an enclosed space like a human body. That is why there is great promise in this idea of magnetic actuation, because it is fast, forceful, body benign, and can be remotely controlled. Other groups have fabricated magnetically activated materials, though the movements they have achieved have been relatively simple. Instead of making structures with magnetic particles of the same uniform orientation, the team looked for ways to create magnetic domains, individual sections of a structure, each with distinct orientation of magnetic particles. When exposed to an external magnetic field, each section should move in a distinct way, depending on the direction its particles move in response to the magnetic field. In this way, the group surmised that structures should carry out more complex articulations and movements. With their new 3D printing platform, the researchers can print sections or domains of a structure and tune the orientation of magnetic particles in a particular domain by changing the direction of the electromagnet encircling the printer's nozzle as the domain is printed. The team also developed a physical model that predicts how a printed structure will deform under a magnetic field. Given the elasticity of the printed material, the pattern of domains in a structure, and the way in which an external magnetic field is applied, the model can predict the way an overall structure will deform or move.